Good morning, all. I hope you can all hear me. I will give you some time to settle. See some colleagues, that's also always good. Clicker, yes, I can use that. Thank you. All right, thank you. Welcome to my tech talk this morning. Can everyone hear me? It's okay. Who's from outside Europe? Hands, please. No, there's one. Okay, that's good. Who is working with pressurized electrolyzers? Some hands, that's good. Okay. Who has ever heard of dome-loaded back pressure regulators from Ikidibach? That's good. Okay, but we still have to do some work. Okay, today we are going to talk about precision pressure control in pressurized electrolyzers. I quickly want to introduce myself. My name is Armand Bergsma. I started in 1999 with a company focusing on mass flow and Coriolis technology. And after working there for 14 years, I discovered, and actually the man who introduced me to it is here, so thank you, Johan, for coming. And I discovered technology from Ikidibach, who provides dome-loaded back pressure regulators, and that made me decide to actually start my own company. So in 2016, I founded Pressure Control Solutions, and we quickly built up the market in Northwest Europe. In 2020, we were with 6-7 people. No 6-7 responses, okay. There's some young people in the audience as well. But that was actually a major turning point in my career, because then COVID hit us, and that was obviously a very bad thing. But I got contacted by a group of students from the Technical University of Delft, and they had to build emergency respirators, because everyone was suffering. There were not enough respirators in the world, so they had to produce one. Their professor said, it's impossible, you cannot go to your thesis, you cannot do any work on that. So he decided we are going to build respirators within 1 month. And that was a truly inspiring moment for me as well, because what we found is that if there is a real urgent problem, then everyone will join forces. And indeed, within a month, they developed these respirators. And we were part of that. And we were part of that because we had to develop a control valve that would help exhale. And from the first phone call until the prototype running in the system took about 25 hours. It's amazing, but that's possible when everyone is joining forces. And to think about that still gives me goosebumps, to be honest, because that was a truly inspiring time. That was also when I realized that you can make a difference. As small as it is, you can still make a difference in the world. And as a company, we were already enabling a lot of engineers with demanding applications. And I felt the same spark at companies that were contacting us regarding electrolysis. And I thought, well, this is something that we can really put effort into it, so we can make that small difference. So since 2020, we have been working, engineering on those applications, because a lot of customers struggled with keeping pressure stable in an electrolyzer. We were already selling dome-loaded back pressure regulators with commercially available pilot controllers. I will go in more detail about that later. But we also thought, well, we have to do this better, because we want to bring the price of nitrogen down. We want to get green energy into the market, and maybe we can contribute to that. So PCS, Pressure Control Solutions, the company I founded, is normally really looking and working with engineers who want to set new boundaries. And that's what we did with a product that we developed, and this is how we came to hydrogen being our focus. So what was a typical question from customers? That was membrane damage should be prevented, cross-contamination should be prevented, and dynamic operation should be possible. So thanks to ChatGPT, we got this nice picture. You probably have seen much better stacks here. But this is what you want to avoid, obviously. You want to have a delta P as small as possible. Even if you run at very high pressures, you still need to have a very small delta P. Another topic is obviously cross-contamination. I don't think I have to explain that to many of you, but you don't want hydrogen to go back into your oxygen, because that's a big risk. Dynamic operation is a thing that is upcoming. We got more and more requests to get to be able actually to get your electrolyzer directly on the grid and to follow the power up and down of your electrolyzer and keep and maintain your production constant. Because we all know weather happens sometimes. So if you are producing green hydrogen from solar cells and you will have a cloud getting in front of your solar cells, then all of a sudden your production will go down. And that can happen pretty rapidly. So it can take a minute to drop from 90% to 10%. And that is something that we set as a benchmark to develop our solutions. So here I have to walk to the screen probably because I don't have a pointer, but on the left side you can see a very simplified P&ID. You probably recognize the electrolyzer itself over here. And you also see two tiny vessels, probably much bigger in your systems, and you see the pressure sensors on top of it. On each side of the electrolyzer, you will have a dome-loaded back pressure regulator. This dome-loaded back pressure regulator was the reason I quit my job and I started to represent this product, which is an Electrolyzer dome-loaded back pressure regulator, which is ideal for these kind of applications because you need huge rangeability. You need to work on the hydrogen with maybe KOH in it. It needs to be able to handle high flows at low pressures and sometimes low flows at high pressure. So you need a huge dynamic rangeability. And a single valve can handle in the rangeability of 1 to 10,000, which is kind of amazing, but it works. So on each side of the electrolyzer, we have a dome-loaded regulator that you can see here, and a dome-loaded regulator for the oxygen side, and you will have a pilot controller, which is the one that we focused on, because the pressure upstream of this regulator is exactly the same as the pressure that you put on top of the diaphragm. Exactly, we still have to compensate it for the last millibars, but it's got a 1-to-1 ratio. That's the most important thing to remember. In the middle, there's a delta P sensor, because we need to measure the delta P over the stack, and we control based on delta P. I've seen a lot of level control systems as well, but we found that delta P is much faster. And actually, if we really want to be dynamic, then we need a really fast delta P sensor, so we developed our own. So the two blue boxes on the right in the P&ID are the EQDA, so that's an electronic pilot pressure controller that is super precise and can control up to 70 bar with a precision of plus or minus 5 millibar. In the back, you see very large valves designed by Electrolyzer for emergency shutdown. One of the critical things is that when you have no power, there is nothing to control. So if you have a complete power failure, you want to depressurize your electrolyzer and you still don't want to damage your stack. So Electrolyzer designed a valve that is purely mechanical, where you have a small vessel at the top that is piloting the two regulators, and as soon as the power fails, the normally opened valve will open and it will just gradually decrease the pressure on two sides of the electrolyzer, staying within a bandwidth of 20, 30, 40 millibar. Explaining the back pressure regulator in a bit more detail for the people who have never seen it. It's pretty simple but brilliant design. If you can see the small holes here in the body, that's where the flow goes to the diaphragm. The diaphragm is closing the flow, and it's closed by the pressure that is put on top of that diaphragm. They are super robust. You can make them out of any material like stainless steel or Monel, and you can take a diaphragm from PEEK or also stainless steel. And the nice thing is that you can increase the number of orifices so that you can scale this up to, well, a CV of 160 for the people who says something, but that's a regulator this size that can handle quite a lot of hydrogen. Then the device that we have been working on for the last 6 years, which is the EQDA, and this is the pilot controller setting the pilot pressure on top of that dome-loaded regulator. What we used is a very high accurate pressure sensor that sits on top of a body. Flow goes in and we control the pressure on the outlet, which is the top of the diaphragm. Two proportional valves are controlling that, and we have a very fast PC board that is actuating the valves all the time. This is the video where I do have to give a little bit explanation, because on the complete left side of this, you see a graph, and that is going to be the stack pressure. So I hope you can see it. It's a 100-inch screen, I've been told, but so we are running the stack now at 0.2 bar. And what you see here is a set point for the stack pressure. What you see here is the control pressure by our device. And what you can see here on the right is the delta P. So we are now controlling within a bandwidth of 0.3 millibar. So not 300 millibar, but 0.3 millibar, and this is a setup that can run up to 10 bar. When we change the set point, and that is going to happen right now, then you can see that there's a pressure increase with a slope function now of 60 seconds. So in 60 seconds, we go from 0 to 10 bar. So in 1 minute to 10 bar, or in 3 minutes to 30 bar, while we stay within a delta pressure of, in this case, minus 13 millibar. And as soon as we hit, what you can see is now that there is an offset, so we are actually tracking with the delta P control in closed loop, we are tracking the stack pressure. And as soon as we hit the pressure at 5 bar, you will see that the delta pressure becomes 0 again. So we are again within the bandwidth. Now we are going to change the load. So on the right side, you will see the hydrogen flow and the oxygen flow, and we drop this now from 90% to 10%. And there is almost no influence on the actual stack pressure. So you can see that the controller has to work, but it is still within 1 millibar. And if you scaled it up to 70 bar, it would be 7 millibar bandwidth. So now we increase the load again to 90% and still no influence on the delta P control because we close the loop really, really fast. Obviously, we also need to go down in pressure at a certain point. First we are going to change the delta P because we have now set it to 0 millibar, but you can also change that and give a set point up for 25 millibar or down as we just did. And you can see that it responds really quickly, so you can actually preset the delta P over your stack. As soon as we are back at 0, we are going to set the set point back to, so we are going to decrease the pressure to 0.2 bar. And we do that at the moment again with 60 seconds. So in 60 seconds, we will go from 10 bar to 0. And the interesting thing, what you see is that the delta P is now tracking it again, and now we have an overpressure on the hydrogen side of 13 millibar. But as you just have seen, we could have set a set point of minus 13 and be just exactly spot on 0 millibar. How aggressive you set this, you can choose that. It's now set at 120 seconds, and if you double the time that you take to decrease the pressure, then you have half of the difference between the set point and the measured value. We can do that again, and now we are at 3 millibar controlling, and now we have 240 seconds. And as soon as we hit 0.2 again, we will be stable, so the red line on this side will drop again, and we are controlling at 0 millibar. So there we go. This was my demonstration. This is my video. We have this live demo. We have it on our booth. So if you want to see it, then this is the booth number in Hall 2 F58. We have the design engineer over there. If you have any super critical questions you want to ask them, that's also possible. And for this event, we created a discount voucher. So for everyone who wants to try it, we want to make that as easy as possible and lower the investment for you. So that's it. Thank you.